Welcome to the part 2 of hydrocarbons, class 11, 9.3 alkenes. Alkenes are unsaturated hydrocarbons containing at least one double bond. What should be the general formula of alkenes? If there is one double bond between two carbon atoms in alkenes, they, uh, they must possess two hydrogen atoms less than alkenes. Hence, the general formula for alkenes is CnH2n. Alkenes are also known as olefins, that is, oil forming, since the first member, ethylene or ethene, was found to form an oily liquid on reaction with chlorine. 9.3.1 Structure of double bond. Carbon-carbon double bond in alkenes consists of one strong sigma bond, that is, bond enthalpy about 397 kJ per mole, due to head-on overlapping of sp2 hybridized orbitals, and one weak pi bond, that is, bond enthalpy about 284 kJ per mole, obtained by lateral or sideways overlapping of two 2p orbitals of two carbon atoms. The double bond is shorter in bond length, that is 124 picometer, than the carbon-carbon single bond, that is 154 picometer. You have already read that pi bond is weaker bond due to poor sideways overlapping between two 2p orbitals. Thus, the presence of pi bond makes alkenes behave as a source of loosely held mobile electrons. Therefore, alkenes are easily attacked by reagents or compounds which are in search of electrons. Such reagents are called electrophilic reagents. The presence of weaker pi bond makes alkenes unstable molecules in comparison to alkanes, and thus alkenes can be changed into single bond compounds by combining with the electrophilic reagents. Strength of the double bond, that is, the bond enthalpy 681 kJ per mole, is greater than that of the carbon-carbon single bond in ethane, that is, the bond enthalpy 348 kJ per mole. Orbital diagram of ethene molecule are shown as in figures 9.4 and 9.5. Here is the figure that you can see. So this is figure 9.4, orbital picture of ethene depicting sigma bonds only. 9.3.2 Nomenclature. For nomenclature of alkenes in IUPAC system, the longest chain of carbon atoms containing the double bond is selected. Numbering of the chain is done from the end which is nearer to the double bond's suffix "ene" replaces "ane" of the alkenes. It may be remembered that the first member of alkene series is CH2 replacing N by 1 in CnH2n, known as methene, but has very short life. As already mentioned, first stable member of alkene series is C2H4, known as ethylene or ethene. IUPAC names for a few members of alkenes are given below. Here you can look the structures as well as the IUPAC name. Here the CH3CH double bond CH2 is propene. CH3CH2CH double bond CH2 is but1-ene. CH3CH double bond CH3 is but2-ene. CH2 double bond CH single bond CH double bond CH2 is buta 1,3 diene. Then CH2 double bond C attached with a methyl group with CH3 is 2-methyl prop 1-ene, and CH2 double bond CH with CH and CH3 attached to CH, and then again a CH is 3-methyl but 1-ene. Here you can look the structures. Moving on, isomerism. Alkenes show both structural isomerism and geometrical isomerism. Structural isomerism. As in alkanes, ethene and propene can have only one structure, but alkenes higher than propene have different structures. Alkenes possessing C4H8 as a molecular formula can be written in following three ways. Here is the first way, then there is the second way, and here is the third way. Okay, so structures 1 and 3 and 2 and 3 are the examples of chain isomerism, whereas structures 1 and 2 are position isomers. Now, geometrical isomerism. Doubly bonded carbon atoms have to satisfy the remaining two valencies by joining the two atoms or groups. If the two atoms or groups attached to each carbon atom are different, they can be represented by YXC double bond CXY like structure. YXC double bond CXY can be represented in the space in the following two ways. Here are the two ways which you can see on the screen mentioned as A and B. So, in A, the two identical atoms, that is both the X or both the Y, lie on the same side of the double bond. But in B, the two X or two Y lie across the double bond or on the opposite sides of the double bond. This results in different geometry of A and B, that is, disposition of atoms or groups in space in the two arrangements is different. Therefore, they are stereoisomers. They would have the geometry if two atoms or groups around C double bond C bond can be rotated, but rotation around C double bond C bond is not free. It is restricted. For understanding this concept, take two pieces of strong cardboards and join them with the help of two nails. Hold one cardboard in your one hand and try to rotate the other. Can you really rotate the other cardboard? The answer is no. The rotation is restricted. This illustrates that the restricted rotation of atoms or groups around the doubly bonded carbon atoms give rise to different geometries of such compounds. The stereoisomers of this type are geometrical isomers. The isomer of type A, in which two identical atoms or groups lie on the same side of the double bond, is called the cis isomer, and the other type of the type B, in which the identical atoms or groups lie on the opposite sides, is the trans isomer. Thus, cis and trans isomers have the same structure but different configuration, that is, the arrangement of atoms or groups in the space. Due to different arrangement of atoms or groups in space, these isomers differ in these properties like melting point, boiling point, dipole moment, solubility, etc. Geometrical or cis-trans isomers of but2-ene are represented below. So you can see the diagram of cis-but2-ene and trans-but2-ene. The boiling point is slightly different and higher in the case of cis-but2-ene. Okay, so cis form of alkene is found to be more polar than the trans form. For example, dipole moment of cis-but2-ene is 0.33 dBi, whereas the dipole moment of the trans form is almost 0. Or it can be said that trans-but2-ene is non-polar. This can be understood by drawing geometries of the two forms as given below, from which it is clear that in the trans-but-ene, the two methyl groups are in the opposite directions. Therefore, the dipole moments of CCH3 bonds cancel, thus making the trans form non-polar. Here you can see how they cancel each other in the trans. That's why the it's considered as non-polar. Now, in the case of solids, it is observed that the trans isomer has higher melting point than the cis form. Geometrical or cis-trans isomerism is also shown by alkenes of the types XYC double bond CXZ and XYC double bond CZW. Moving on to 9.3.4 preparation. From alkynes, alkynes on partial reduction with calculated amount of dihydrogen in the presence of pelletized charcoal partially deactivated with poisons like sulfur compounds or quinoline give alkenes. Partially deactivated pelletized charcoal is known as Lindlar's catalyst. Alkenes thus obtained are having cis geometry. However, alkynes on reduction with sodium in liquid ammonia form transalkene. So you can see the examples here. This alkene with palladium, with the presence of palladium, forms cis alkene, whereas in the other example it shows that it forms a trans alkene with the change of the enzyme. Like if we are using pelletized charcoal partially deactivated with poisons, and the poisons can be sulfur or quinoline, then it is making cis, else it is making trans. I hope that you have seen these equations. Now, will propene thus obtained show geometrical isomerism? Think for the reason in support for your answer. Second preparation. From alkyl halides. Alkyl halides on heating with alcoholic potash, that is potassium hydroxide dissolved in alcohol, say ethanol, eliminate one molecule of halogen acid to form alkenes. This reaction is known as dehydrohalogenation, that is the removal of halogen acid. This is example of beta elimination reaction. Since hydrogen atom is eliminated from the beta carbon atom next to the carbon to which halogen is attached. Now you can refer to this image for your practice. Okay. Now, nature of halogen atom and the alkyl group determine the rate of the reaction. It is observed that for halogens the rate is iodine, bromine, chlorine, while it is observed that for halogens the rate is iodine greater than bromine greater than chlorine, while for alkyl group it is tert greater than secondary greater than primary. Third preparation. From vicinal dihalides. Dihalides in which two halogen atoms are attached to two adjacent carbon atoms are known as vicinal dihalides. Vicinal dihalides on treatment with zinc metal lose a molecule of ZnX2 to form alkene. This reaction is known as dehalogenation. Here you can refer to the equations. Fourth preparation. From alcohols by acidic dehydration. You have read during nomenclature of different homologous series in Unit 12 that alcohols are the hydroxy derivatives of alkanes. They are represented by ROH, where R is CnH2n plus 1. Alcohols on heating with concentrated sulfuric acid form alkenes with the elimination of one water molecule. Since a water molecule is eliminated from the alcohol molecule in the presence of an acid, this reaction is known as the acidic dehydration of alcohols. This reaction is also an example of beta elimination reactions, since OH group takes out one hydrogen atom from beta carbon atom. Here you can refer to the equation. Moving on, 9.3.5 Physical properties. Alkenes as a class resemble alkanes in physical properties except in types of isomerism and difference in polar nature. The first three members are gases, the next 14 are liquids, and higher ones are solids. Ethene is a colorless gas with a faint sweet smell. All other alkenes are colorless and odorless. Insoluble in water, but fairly soluble in non-polar solvents like benzene, petroleum ether. They show a regular increase in boiling point with increase in size. That is, every CH2 group added increases boiling point by 20 to 30 Kelvin. Like alkenes. Straight chain alkenes have higher boiling point than isomeric branched chain compounds. Chemical properties. Alkenes are the rich source of loosely held pi electrons, due to which they show addition reaction, in which the electrophiles add on the carbon-carbon double bond to form the addition products. Some reagents also add by free radical mechanism. There are cases when under special conditions alkenes also undergo free radical substitution reaction. Oxidation and ozonolysis reactions are also quite prominent in alkenes. A brief description of different reactions of alkenes is given below. Addition of dihydrogen. Alkenes add up one molecule of dihydrogen gas in the presence of finely divided nickel, palladium, or platinum to form alkenes. Number 2. Addition of halogens. Halogens like bromine or chlorine add up to alkene to form vicinal dihalides. However, iodine does not show addition reaction under normal conditions. The reddish orange color of bromine solution in carbon uh, tetrachloride is discharged when bromine adds up to an unsaturation site. This reaction is used as a test for unsaturation. Addition of halogens to alkenes is an example of electrophilic addition reaction involving cyclic halonium ion formation, which you will study in higher classes. Here are the reactions you have to refer. You can refer. Yeah. Third, addition of hydrogen halides. Hydrogen halides like HCl, HBr, HI add up to alkenes to form alkyl halides. The order of reactivity of hydrogen halides is HI greater than HBr greater than HCl. Like addition of halogens to alkenes, addition of hydrogen halides is also an example of electrophilic addition. Let us illustrate this by taking addition of HBr to symmetrical and unsymmetrical alkenes. Addition reaction of HBr to symmetrical alkenes. Addition reaction of HBr to symmetrical alkenes is similar, that is, the similar groups attached to double bond takes place by electrophilic addition mechanism. Here is the reaction that you have to refer. Moving on. Addition reaction of HBr to unsymmetrical alkenes, that is Markov-Vinokov's rule. Now, how will HBr add to propene? The two possible products are 1 and 2. Here you can refer to these possible products, that is 2-bromopropane and 1-bromopropene. Now, Markovnikov, a Russian chemist, made a generalization in 1869 after studying such reactions in detail. These generalizations led Markov-Vinokovnikov to frame a rule called Markov-Vinokov's rule. The rule states that negative part of the addendum, that is, adding molecule, gets attached to the carbon atom which possess lesser number of hydrogen atoms. Thus, according to this rule, product 1, that is true 2-bromopropane, is expected. In actual practice, this is the principal product of reaction. This generalization of this generalization of Markovnikov's rule can be better understood in the terms of mechanism of the reaction. Now we are here to learn the mechanism, so moving on with the mechanism. Hydrogen bromide provides an electrophile H+, which acts the double bond to form carbocation as shown below. You can see which one is the most stable and which one is the less stable. So, the secondary carbocation B is more stable than the primary carbocation A. Therefore, the former predominates because it is formed at a faster rate. The carbocation B is attacked by Br minus ion to form the products as follows. You can see that 2-bromopropane is the major product. Moving on. Anti-Markovnikov addition or peroxide effect or Kharash effect. In the presence of peroxide, addition of HBr to unsymmetrical alkenes like propene takes place contrary to the Markovnikov's rule. This happens only with HBr but not with HCl and HI. This addition reaction was observed by M.S. Kharash and F.R. Mayo in 1933 at the University of Chicago. This reaction is known as the peroxide or Kharash effect or addition reaction anti to Markovnikov rule. So here is the reaction you have to refer. Mechanism. Peroxide effect proceeds via free radical chain mechanism as given below. So you can see that benzoyl peroxide under homolysis produce the following the following compound. Yeah. So these are the reactions. Moving on. This is the last reaction you have to see over here. The secondary free radical obtained in the above mechanism, that is the step 3, is more stable than the primary. This explains the formation of 1-bromopropane as the major product. It may be noted that the peroxide effect is not observed in addition of HCl and HI. This may be due to the fact that HCl bond being stronger, that is 430.5 kJ per mole, than HBr bond, that is 363.7 kJ per mole, is not cleaved by the free radical, whereas the HI bond is weaker, that is 296.8 kJ per mole, and iodine free radical combine to form iodine molecule instead of adding to the double bond. Fourth, addition of sulfuric acid. Cold concentrated sulfuric acid adds to alkenes in accordance with Markovnikov rule to form alkyl hydrogen sulfate by the electrophilic addition reaction. Here you can refer to this and this. So moving on. 5. Addition of water. In the presence of few drops of concentrated sulfuric acid, alkenes react with water to form alcohols in accordance with the Markovnikov rule. So you can here refer to the reaction. Moving on. Oxidation. Alkenes on reaction with cold dilute aqueous solution of potassium permanganate, which is the Bayer's reagent, produce vicinal glycols. Decolorization of KMnO4 solution is used as a test for unsaturation. So here is the reaction you have to refer. Now B. Acidic potassium permanganate or acidic potassium dichromate oxidizes alkenes to ketones and or acids depending upon the nature of the alkene and the experimental conditions. Here are the two reactions that you need to refer. Then now the 7th is ozonolysis. Ozonolysis of alkenes involves the addition of ozone molecule to the alkene to form ozonide, and then cleavage of the ozonide by ZnH2O to smaller molecules. This reaction is highly useful in detecting the position of the double bond in alkenes or other unsaturated compounds. Here you can refer to these reactions and this one. Yeah. Moving on to the eighth one, which is polymerization. Polymerization. You are familiar with polythene bags and polythene sheets. Polythene is obtained by the combination of large number of ethene molecules at a high temperature, high pressure, and in the presence of catalyst. The large molecules thus obtained are called polymers. This reaction is known as polymerization. The simple compounds from which the polymers are made are called monomers. Other alkenes also undergo polymerization. Here are the reactions that you need to refer. Now, polymers are used for manufacture of plastic bags, squeeze bottles or refrigerator dishes, toys, pipes, radio and TV cabinets. Polypropylene is used for manufacture of milk crates, plastic buckets and other molded articles. Through these materials have now become Though these materials have now become common, excessive use of polythene and polypropylene is matter of great concern for all of us. Thank you for watching this. We have successfully completed the alkenes, and now in the next part we'll do alkynes and then the other part. So in the next part we'll end up this chapter. Thank you for watching and keep learning. Thank you.